Right, I just saved some changes. Keep saving changes.
Yep, there you go. Hold on, let's see if we can get rid of that Dropbox.
The moment you do that, I think my clicker will stop working. Yep.
There you go. All right.
No clicker.
Try it now. Hey, there you go.
There you go. I think. Okay, so quick recap. This is the story that we had. We were speaking of an agent in an environment where the entire interaction was something like this. You had an environment which we had an agent operating in an environment who took actions. The actions changed the environment, and the agent observed the modified environment and got some rewards in the process from the environment. So the agent had to decide how to act at any time in order to maximize the agent's rewards. So we started off by speaking about whatever my clicker will show me, which is yes. We started off by speaking about a Markov processes where the state of the future of the system is governed entirely by the current state of the system and not anything that happened in the past. We also showed how any system where the future is dependent on some finite history can be modeled as a Markov process by defining what I called a Markov state, but really should be called an information state, where if with a proper appropriate definition of the information state, the entire process can now still be modeled as Markov. So here, for example, in the case of Glider, Flighter's brother, who never turned back, the future was decided by the edge the spider walked up and the direction in which the spider walked. But if you use that as your information state, then the future became independent of everything that happened prior to traversing that edge. So we have a problem with this clicker, which is not really.
It's working sometimes.
Yeah, stochastic.
Try now.
No.
All right. We can advance the slides here, but I'll see if it's batteries.
Okay, I think it's the batteries. Let me speak from here for a while we're fixing that. Okay. So how do I just use the arrows?
Yeah.
Okay. And so we defined a Markov process like so. It's a random process where the future is only defined by the present. It's memoryless. And it's fully defined by a set of states and a state transition probability and a set of state transition probabilities which specified the probability of the future state given the current state. You needed the specification of the complete set of states that the process had and the complete set of state transition probabilities. But once you had these, then the Markov process was fully defined, right? So, and we also saw that we could write the state transition probability matrix in this manner, where P, Si, Sj is the probability of going to Si in the next step, given that you are currently in Sj. Beautiful. Okay. So, wait.
Maybe it's the receiver. Try now.
That's really bizarre. I have to stand here and do it. Okay, no biggie. Okay. So then we also began by defining a Markov reward process. This is where we ended in the last class. A Markov reward process is a Markov process where states give you rewards. So upon arriving at any state, you obtain a reward drawn from a distribution at that state. So here was an example of a Markov reward process. The spider is walking along the edges of the cube again, but at each corner there is a little swarm of flies. And so when it arrives at any corner, it has a probability of grabbing a flies of different sizes based on the swarm at the corner. So the fly receives a reward at every corner. So just by coming to a corner, there's a reward. This was what we call a Markov reward process. So was this a Markov reward process by that definition? We saw it was, because although the spider doesn't really get any real reward at 7 of the 8 corners, at the 8th corner there is a reward. And you can think of having a reward of 0 at 7 of the 8 corners. So there's a probability distribution over rewards at 7 of the 8 corners, where the distribution has a probability, where a reward of 0 has a probability of 1, and all other rewards have 0 probability, right? So formally, a Markov reward process is the tuple defined now. We just took the standard definition of a Markov process and expanded it. Now the tuple includes a set of states, transition probabilities, which can be expressed as we saw as a matrix, and now a reward function which consists of a probability distribution over rewards at each state. So like the swarm of flies. And instead of speaking of the reward of the probability distribution, we will see that we can just speak of the average reward at each state. And as far as our discussion is concerned, the two definitions are equivalent, at least for the purposes of the computations that we will be performing. And then finally, we defined a discount factor between 0 and 1. And what was the point of the discount factor? So let's go back and look at this. Okay, so here, in fact, before talking about this, right? No, that doesn't work. I have to come there and stick my clicker into it. Okay, so let's say there were different reward distributions at each corner, right? Then we need to have some idea of which path is going to be most promising. So consider this. I'm sort of peeking a little bit into the future, but remember that when we spoke of the chess game, when we went to the end of the game and won a game, we had to attribute that victory to the moves we made in the past. And as we went further and further in the past, we could attribute less and less of the victory to the position that you were in way back in the past. So whatever you did in the first move was much less likely to have had a direct influence on the current outcome than what you did in the last move just before the game ended. So this was the idea behind this notion of discounting. How much do you want to actually attribute the current victory to something that happened way back in the past? This was in the chess game. Now you can flip around and you can say, what do I think is going to happen in the future? And whatever you see in the immediate future is probably much more predictable than what happens later in the future. And so we need a discount to account for this. We'll revisit this in a few minutes. But then here's what we are really interested in. Over all the future, at any point, we are interested in knowing the total reward that we are going to get from here on out all the way into the future. So because that's what you really want to maximize. So if you're at time 0, then you want to maximize the sum of the reward at time 1 plus time 2 plus time 3 all the way into whenever the game ends or whenever the whole process ends. And this is what we will call the return. So there's a distinction between what we call a reward and what we call a return. Now, when I arrive at any state, when the spider arrives at any state, it's going to grab a fly. That is the reward it got for arriving at the corner. But then, if the spider is at any particular corner, it can expect to continue to get rewards into the distant future. So the total sum of rewards all the way from here on to infinity is the expected return, or is the return that the spider gets for being in that state. So consider this, this process over here. If the spider is in corner 1, what would you expect the reward to be? Let's say, maybe I should go back one slide just to. So let's say if the spider is, let me pick something sufficiently sparse, right? So if the spider is in corner 2, what would you, versus the spider being in corner 1, where would you expect to see the greater reward? in 2 because 2 has many more flies, right? But then if I spoke of a return, the total reward all the way into the future, which of the two is going to be better in your opinion? 1, because 1 is closer to the big swarm of flies at 4, right? So also if you compare 2 versus 3, clearly the rewards at 2 are much greater than the rewards at 3. But the returns at 2 are much greater because from 3, the next step, you can just go to 4, and then you're going to keep gobbling lots and lots of big fat flies. Whereas if you're at 2, you're just you have to travel some distance before you actually end up in a nice juicy spot. So there's a distinct difference between the immediate reward and the return, which is the sum of all rewards all the way into the future. So this is the first distinction we want to make. This guy here is the return, which is the sum of rewards, and each of these terms is a reward at one particular turn. Okay. So the long-term, I'll just skip the slide. So here is what we call the discounted return. The discounted return is the total future reward all the way to the end, except we are not simply going to sum up all of the rewards. We are going to we are going to scale each of the future rewards by some term gamma. Okay. And now what is the magic of this gamma? So let me peek into a little bit into the future for the lecture itself. Let's say you are at some corner. So you have this, the spider lives in this cube, as we know, right? And let's say the spider is at this corner, and then it travels around. Okay. So if it travels around at time t equals 0, the rewards it saw are R1, R2, R3, R4, R5, R6, R7, R100. Maybe it stopped playing at 100. Okay. So now it goes back and thinks about what happened at time 0 and says, okay, at time 0, this is the sequence of rewards I got. So is the sum of all of these terms a typical sample of what I would expect to see as the return, not the reward, at time 0? If, right? So this is the question the spider is really asking itself. Okay, I've had this experience. I've gone from 0 through 100. Now let me go back and think about what happened at time 0. And I got this series of rewards, R1 through R100. Is that sum what I can expect? Is that typical of what I will see if I am at wherever I was at time 0? And now go back and think about the chess game, right? This is exactly the inverse of the chess game. Instead of instead of looking back from the victory, you're looking forward from t equals 0. But the fact remains that the distant future is much fuzzier than what happens over here, right? So if this is what you observed, you expect this guy to be typical. You expect this guy to be more typical, right? You expect this guy, which happened after a lot of wandering, to be far less typical of what you would expect to see if you repeated the process all over again. Did that make sense to you guys? Right? So in other words, as you go into the future, you want to weight this guy less and less. So you want to say the actual return is going to be some R1 plus, let me say, gamma 1 R2 plus gamma 2 R3 and so on and so forth till gamma 99 R100, right? The reason I'm doing this is you're going to weight things in the future less and less and less as being typical of the experience you had at time equals 0. I haven't written this as gamma raised to 99, just observe that, okay? I've just written this as gamma 99, although on the slides I've written this as gamma raised to 99. We'll get back to why the distinction between the two. But then if you just decide that gamma raised to 99 or gamma k equals gamma raised to k, some constant gamma raised to k. This gives you the behavior that you see on the slides. And now what is the behavior that you actually want to see for these gammas? As you look further and further into the future, you want to trust what you saw less and less and less. So you want the gammas to go down as a function of time. And making them go down exponentially is a natural way of modeling things. You could also use other mechanisms, but making them go down exponentially is kind of natural over here. So if you use this exponentially, if you use this exponential scheme for gammas, then if I say gamma equals 0, you're saying the future is totally unpredictable. Basically, everything that happened from R2 on is not typical of what I expect to see if I repeat the experiment. If I say gamma equals 1, I'm going to say that entire sequence was so typical, so typical, so typical that if I repeated it, I can expect the same kind of behavior again. So this gamma term is a measure of your trust in what you observed in the future as being typical of what you can expect to observe if you repeated the experiment. Right? Okay. So that gamma is part of the Markov reward process. Now observe that there's a little bit of weirdness over here in that there's a little indexing problem. At time t, you're always indexing the rewards from time t plus 1. This is just convention, but we'll stick with it. Okay. So here, let's say I have this example. My spider went wandering around the corners, and at time 0, these are all the things that happen to the spider. Okay. What is the reward at time 1? 1. Okay. What is the reward at time 7? The reward, not return. 1.2, right? So you see that these are rewards. The rewards are what it got at each turn. Okay. Now, what is the how were these rewards actually obtained? There was a swarm of flies at each corner. It grabbed a reward, grabbed a fly, right? So these are these sample rewards or expected rewards? Samples, because this is one experiment. It actually walked through the corners till it died, and so at each turn it actually got a fly, and so these are sample rewards. These are the samples that it obtained. Does this tell you anything about the expected reward? If many spiders walk through the same 100 sequence, on average, what would they expect to see at each turn? This doesn't tell you anything about the two. What is the condition under which the expected reward would be the same as the sample reward? The distribution is just a delta. There's just one fly at each corner, right? In that case, each sample is also going to be the expectation, because you have only one value at each corner. But if you have a distribution at each corner, then anything that you get is going to be a sample drawn from the distribution. So this is, fairly straightforward, okay? But now, what is the return at, so I'm going to use this notion, symbol G to indicate returns and the symbol R to indicate rewards. So what is the return at time 1? Actually time 0 using our indicator. Okay, let's say, what is the return at time 1? No, the return is the sum. So before that, you're going to ask me, what is the gamma? So if I say gamma equals 1, what is the return at time 1? No, because you remember, you're always adding from the next time, right? The way we indexed it. The return at time 1 starts with the rewards at time t plus 1, which is 2. So the return is going to be 2 plus gamma times 0.7 plus gamma squared times 1.2 plus gamma cubed times 0.5 plus and so on. So which is going to be 2.7, 3.9, 4.4, 7.4, 8.6, 10.6, 11.6. Okay, so the return at time 1 using gamma equals 1 is 11.6. Make sense to you guys, right? What is the return at time 7? Okay. 3, right? Now suppose I change the gamma to 0.5. What is the return at time 7? 2.5, right? If the gamma were 0.1, what would the return at time 7 be? 2.1. It's going to be 2 plus 0.1 times 1, right? If the return were 0.5, what is the if gamma were 0.5, the discounting factor were 0.5, what is the return at time 6? Anyone? So it's going to be 1.2 plus 1 plus 0.25, right? So that's 3.6 plus 0.25, 3.85, right? Am I right? Okay, I'm just adding this stuff up, right? But you get the idea of what I'm doing over here. And why are we doing this again? So, and these are all, again, are these sample returns or expected returns? Sample returns. So even the returns are actually a probability distribution, a random variable which have a probability distribution, correct? Because you have these distributions at these various corners, and in any given step when you're wandering through the whole process, you're going to be adding up these discounted rewards you got as you walk through, and that is a random variable by itself. What I mean by this is that if you had a different spider walking the exact same sequence of steps, and then you just looked at the returns that the two spiders got, they're going to be different. If I had millions of spiders walking the exact same sequence of steps, each of them is going to get a different return, but there will be a probability distribution, right? You can say, what is the probability that the next spider that walks the exact same sequence of steps is going to get a return of 8? And you can answer that question, right? So this is also, and so this one is actually what everything that we are looking at over here is a sample return. But if there were a unique reward at every corner, what you would get is an expected return. Can somebody tap him? He's falling asleep, or he's not falling asleep, he's sound asleep. So, okay. Considering that the slides won't be up and it'll, and you know, you should, okay. Here was my question, right? Now, and now what is this new notion? We've sort of discounted sample returns at any time. They have a fuzzy sort of meaning. But if you really want to, but to really understand why we are using the discounting, you have to go back to this, right? That when you're counting the return at any point, you want to be less and less certain about what you saw in the future when you go back and revisit your experience. So, and it's also very important to realize that a specific sequence of rewards was really just drawn from a distribution, that if you repeated the experiment many times, you're going to get different rewards, different returns, and there's an expected return, which is the average over all of those returns, which is really what you're interested in if you're just trying to, you know, if you're trying to optimize your actions, as we will see later on. So here is a spider. This spider over here gains a reward of value 1 if she consumes the fly, okay? The spider has infinite patience. Now, given this, what is the return from any corner? Anybody see that? Right? But you didn't ask me a question. You couldn't have just answered that question. What's gamma, right? If gamma was less than 1, the return, you can't answer that question so trivially. But if I told you that gamma was 1, then the return is always going to be 1, right? If gamma is less than 1, it's going to be what? 0. Yeah, but then you sum them all up. If you take the expected return, it's so you'll have to, it's a geometric series that sums to, I think, gamma, right? Anyway, so regardless of which corner the spider starts from, the spider is going to have a return of 1, right? So in this case, is there a difference between an expected return and the sample return? No, because there's a unique answer, right? When it finally gets the fly, it's going to get a reward of 1, and you're guaranteed that no matter where the spider starts from, it's going to get a reward of 1. So now I can define an expected return E of G, right, for any state S, and what is this value going to be for every corner? There is no gamma, right? I said gamma equals 1. So anybody, we told what's the expected return from every corner, any corner? It doesn't matter which corner the spider starts from, eventually it's going to catch the fly, correct? In other words, the return at any corner is just 1, which is the expected return also, correct? So over here, it's literally going to say the expected return equals 1 for all S. Now, let me change this. Regardless of which corner the spider starts at, she will eventually randomly nab the fly. So the expected return from any corner is going to be 1, correct? Now, let me change the game if I can actually get my clicker to work. Oh. But here. So I'm going to do, so here's what I will define. I'm going to define something called the value of being at a corner. And what is the value of being at a corner? The value of being at a corner is the expected return if you start off at that corner. So the value of every corner in this case is 1, because it doesn't matter where the spider starts from, she's going to catch the fly. So in other words, if you were to just drop the corner spider on the room and ask the spider, where do you want to start? The spider doesn't care. So she's going to say, drop me at any corner. All of them are equally good. All of them have a value 1, right? Now, let me change this a little bit. I'm going to say the spider is hungry, okay? And when the spider is hungry, spiders have finite lifetimes. The longer they go hungry, the closer they are to dying. And because each of the edges is going to take her 1 minute to walk, she gets a negative reward of -1 for every minute she spends finding food, right? In this situation, if I ask the spider, which corner do you want to be dropped in? What's her answer going to be? 8, because she really wants to get the fly. She doesn't want to be spending time catching the fly, right? Now, so you can also assign, in this case, some notion of how bad it is to start at each corner, right? So let's say, what is the value of being in corner 1 now? No. So here, this is getting to be bothersome. Okay. So the value of a state is the expected total discounted return when the process begins at that state. Okay. And here, for example, what is the value of starting in state 1? It's definitely not 1, right? What about the value of starting in state 2? Do you expect it to be greater than the value of 1 or less than the value of 1? Greater, because it's closer to the fly, right? What is the value of state 4, starting in state 4? Is it going to be worse or less than 1? Worse. And it's going to be even worse than 2, right? And it's going to be much, much worse than 8. So because the farther away you are from the fly, the more the spider has to work to get to the fly. But can we actually assign numbers to these values? To do that, first let's go back and look at some definitions. The value of a state is the expected total discounted return when the process begins at that state. So if the process began at state S0, right? The value, or if the process at time 0, if the process began at state S, what is the expected return that the agent has, in this case the spider? Now observe that this is a Markov process, so it doesn't matter what the time is, right? If the current state is currently S, then the expected return is always going to be the same, because it's a Markov process. The entire process only depends on where it currently is and doesn't depend on how it got there, right? So the value for a state S doesn't depend on the time, it only depends on the state S, and is the expected return for the agent, in this case the spider, if the agent is currently at state S. Okay. Now let's go back and answer this question of can you?
We can advance it.
Okay, please advance. Okay. So now let's go back and look at this problem. There's a total reward penalty associated with each corner, right? -1 if the corner has no fly. Why? Because if the spider is at the corner at any corner and the corner has no fly, it is definitely going to spend at least 1 more minute catching the fly. So the reward for being at any corner is -1 if it's not corner 8. -1, and then the return is going to be -1 plus whatever extra effort it takes to catch the fly, right? If it's at corner 8, then it catches the fly. The reward is a 1. Okay? So now I can actually say that my room is not a perfect cube. That the room has a rectangle, I mean, is a cuboid. Some edges are longer than the other edges. In which case, what would happen? The edge that I walk on is going to change the reward, right? So in that case, the reward is no longer associated with the corner. It's associated with the transition, with the edge. But it fundamentally doesn't change the problem. So we're going to assume that rewards are associated with being at corners. That makes sense to everybody, right? So, but we're still speaking of the rewards. And now let's speak of the returns. Here's the hungry spider, right? What is the return for being at corner 1? This is a familiar problem, right? If I'm at corner 1, if it's at corner 1, it's definitely going to spend 1 minute to get to another corner, which could be 2 or 3 or 4, right? And there's an expected return from each of those 3 corners. Correct? So this is the old problem that we just saw. The expected return of corner 1 is the -1 that it spent getting to the next corner because corner 1 had no fly. And then from there, that -1 could have been spent either going to 2 or to 3 or to 4. Each of them has a probability of 1/3 in our example, right? So the expected return is going to be 1/3 of the sum of these 3 guys. What is missing in this equation? Anyone? Gamma, right? Because if the spider is at corner 1, it wants to be less certain of the future. So in other words, the expected return really should have been -1 plus 1/3 times gamma VC2 plus 1/3 times gamma VC3 plus 1/3 times gamma VC4, right? But here we're simply going to be assuming that gamma is 1. And in this problem, it's a natural fit. And why it's a natural fit is that there is a very definitive end to the game. It's going to catch the fly at some point, okay? The spider might die, yes, one of those two. But there's a natural end to the game, right? So in this case, it's kind of a natural fit. But you see, I can now, just using these formulae, I can compute the value of being at every corner. And I can even assign how much better it is to start off at any corner versus starting off at any other corner. And each of these numbers is the expected return from being at the corner. So the notion of expected return sort of makes sense to you guys? So let me change this to a slightly different game. Okay, let's go back and go to this case where the spider, every corner has a swarm of flies. Now, if every corner has a swarm of flies, then what is the expected return of starting at corner 1? So now here you're going to assume that after arriving at the corner, it's going to grab the fly. So the reward is associated with the next time instant simply because of our convention, right? So if it's currently, the spider is currently at this corner, the expected return is going to be, the expected value of the reward at this current corner plus gamma times the reward that it's going to get from the next corner plus gamma squared times the reward that it's going to get from wherever it goes to from that corner, and so on. Correct? And we want gamma to be less than 1. We want to give less importance to the immediate to the future than to the present. And we'll see why that is the case. But then, so now in this case, here is how I could actually write down the equations. Right? The return from any corner is going to be the expected reward at that corner plus gamma times the expected reward from all the corners that it can get to, which in this case is going to be gamma times 1/3 VC2 plus 1/3 VC3 plus 1/3 VC4. Right? Anybody? So wherever it is right now, Because when I'm computing observe that these guys are actually expected returns. These are the values of the future corners. You're not speaking of the rewards, right? So this one in turn has already accounted for the discounting of all of its futures. So the value of being in any corner is going to be the reward it's going to get immediately, plus the discounted expectation of the values of the corners it can possibly get to, right? And what happens if gamma equals 1? What is the answer going to be? Over here? Anyone? If gamma were 1, what would the answer be? Just think about this. Gamma is 1. What is the return? How did we define the return? The reward plus the next reward plus the next reward plus the next reward. Does the game end? Does the spider ever stop walking? So what is the return from being at any state? Infinite, right? So in other words, if I define things in this manner and I said gamma equals 1, it doesn't matter where the spider starts. Eventually, it's going to die of a burst stomach, right? So this is just writing it with gamma equals 1 doesn't give me any mathematical insight into the relative usefulness of corners over here, because it doesn't matter where you start. If the future is less important, as important as now, the total reward, the return from in any corner is going to be infinity, right? So for this whole arithmetic, what would you want it to be? How would you want to set the arithmetic up? Here's how we define the sample return, right? The sample return is going to be, at any time t, is going to be the sum of the discounted rewards all the way into the future, right? And of course, the value of any state is going to be the expected value of the sample return if you begin at the state, right? Now, I can write this. This is basically, so this is just the equation we saw earlier. The value of any state is going to be the reward at that state plus the expected value of all the states you can get to from that state discounted by a factor gamma. This was just the exact same thing that I spoke of for the fly a second earlier, right? A few minutes earlier. Wait, I am missing there's some slides missing. For some reason, my slides are missing. And now observe this guy. For this term to work, right, let's say there's an upper bound on the reward I get at any corner, right? So the sample reward at any time, so the sample return at any time gt be summation k equals 0 to infinity gamma raised to k r of t plus k, and let's say r is always less than or equal to some maximum value m, right? So this is going to be less than or equal to m times summation k equals 0 to infinity gamma raised to k. So for the return to be finite, what's the requirement? This term must be finite. This summation must be finite, right? So in other words, you don't actually need an exponential series. You could take any kind of discounting series which sums to a finite number, and this would work. We just use the exponential series because it's mathematically convenient in this process, okay? So now let me go back and look at the same equation. I can write this equation in vector form. So if I have n states in my process, I can write down the values for the n states like so, right? It's going to be the rewards for the n states plus gamma times the transition probabilities times the rewards for the n states, right? This is just writing the equation that I had. This is what we will call the Bellman expectation equation. And this is just the Bellman expectation equation in matrix or vector form. And now suppose I give you a complete specification of the Markov reward process. I give you the gamma term. I give you all of these transition probabilities. I give you all the rewards, right? And then I ask you to find the value of every state. You have to solve this equation. And you can solve this easily enough if you're, I can just write this. Given the entire process, I can say V equals R plus gamma times PV, where V is the vector of values. And solving for it, V is going to be, I minus gamma P inverse times R. So you can actually compute the value for each state. Now, this is, of course, very easy to write and very easy to solve when you have the spiders problem with only 8 states in the room. But in typical real life problems, like in a chess game, you have 10 raised to 120 possible states. So you're not going to be able to this matrix is going to be 10 raised to 120 squared, and you're not going to be able to invert it, right? But there's a closed form, nice closed form solution. If I completely specify my Markov reward process with the rewards specified for every state, the transition probabilities, and the discounting factor, you can actually tell me what the value of every state is by solving this equation, right? But then now, let's move on to our next process, which is where life becomes real fun, which is Markov decision processes. Now, there's something fundamentally broken about the way I defined the spider and fly problem. Is that how you would expect real life to behave? Is the spider going to be completely random at every corner? Right? Assuming the spider is behaving randomly is assuming the spider has no agency. It can't decide. It's just, doing some random stuff. But if you are a spider and you are at a corner, what are you going to do? You're going to head towards the fly, right? If you're the fly and you see the spider coming towards you, what are you going to do? You're going to get the heck out of there, right? So the way we defined it sort of lost this key aspect of the whole problem, where the agent has a reason to behave in some manner, and the agent is not random. But the environment, in this case the fly, is going to respond to the agent, right? So let's make the agent more intelligent. The agent actively chooses which way to move. So the agent takes action. The agent is not just going to wander, randomly wander. The agent takes action. So in this case, the agent is going to decide which edge to travel on. Okay. So ideally, it would move in the general direction of the fly. But each time the spider moves, the fly is going to respond. Okay. So the agent's action changes the environment. And now let's see how we can model this guy. So here's how I'm going to define this problem. First, what are all the actions the agent can take? The agent can walk in one of 6 directions. Not all of them are going to be possible from every corner, but the total set of actions is 6, possible actions is 6, right? 6 different ways in which the agent can move. So here's what we're going to define it. The agent can decide on one of 6 directions to move in. The spider moves in any of these directions, but then the fly is going to jump, and the fly arrives at a new state, but the state it arrives in depends on where the fly jumped to, which depends on the direction in which the spider moved, right? So basically this is how you'd expect a system like this to behave. If the fly feels threatened, it's going to jump. If it doesn't feel threatened, why does it care, right? There's a spider, it's going away towards, Philadelphia. I don't mind, right? So the spider's action modifies the state transition probabilities in some manner. So how are we going to model this whole process?
Are we saying the fly's direction is random, but the spider chooses?
I'm going to assume that the fly is kind of bouncing randomly, okay? You could actually make the fly a little more intelligent, but eventually you have to give the spider a chance of catching the fly. Otherwise, it's a useless system, right? All spiders are dead, and Darwinian evolution, eventually you're going to get a new type of spider which can figure out how to catch the fly. So anyway, so how are you going to model the system? First, observe that I'm going to define the actions. There are 6 possible actions, and the action the spider takes changes the state of the system, changes the manner in which the state of the system changes. So the transition probabilities depend on the action the spider takes. So can we define it in this simple manner? It turns out this is a trick question. You have to change the manner in which you actually define the system to really model it properly. Okay? And so we're going to define the system. What is the key aspect of this system? If there's a spider trying to catch a fly, what is the most important component of this system? Anyone? It's going to be the distance of the spider from the fly, right? It doesn't matter. I can rotate the room around. It doesn't really matter. The only thing that matters is the relative arrangement of the spider and the fly. So the key component of the system is the direction of the spider, of the distance of the spider from the fly. And so now I can, turns out that there are only 4 states in the system, not 8. Either the spider is at the fly, the distance is 0, or the spider is 1 step from the fly, or the spider is 2 steps from the fly, or the spider is worst case 3 steps from the fly. So there are only 4 states to the system, and here is what the actual information state of the system is, if I want to model it like so. Again, observe, there were multiple ways of defining the information state of the system. Some of them are more useful than others. If I define the information state of the system as the corners, things didn't quite work. I had to define the information. So even if the fly were not moving, I could define the information state of the system either in this way or by defining the corners of the room as my state. If the spider begins, if the fly begins to move, that definition doesn't really help me. So let's look at this guy, right? So now over here, if the fly is spider is at a distance of 3 from the fly, what is the probability, what are the transitions it can make? If the fly is not moving, regardless of where the fly is, regardless of the configuration of the room, if the spider is at a distance of 3 from the fly, that's the maximum distance, right? Any move is going to reduce the distance to 2 with a probability of 1. So from here, from S3 to S2, the transition probability is 1. And what is the reward for being at S3? Definitely has to walk a step, right? It's -1. Now suppose the spider is at a distance of 2 from the fly. What are the transition probabilities? So if the spider is, let's say, out here, right, in this place, there are 2 ways in which it can get closer to the fly and 1 way in which it can get further away from the fly, correct? So there's a transition probability of 1/3 that it's going from S2 back to S3, and a probability of 2/3 that it's going from S2 to S1. And the reward of being at S2 is also -1, because it's going to spend a minute trying to catch the fly, right? Yes?
So if we said that the spider was intelligent, wouldn't it always choose?
Let me get to that, right? So I'm still speaking of this old dumb system. I haven't yet introduced agency and intelligence into the system, right? So now let's say the spider is at a distance of 1 from the fly and it moves randomly. There are 2 ways in which it can actually go away, and when it goes away it can get to a distance of 2, and 1 way in which it can actually get to the fly, right? So from here it has a transition probability of 2/3 to get back to S2 and 1/3 to get to S0. And the reward at S2 is going to be, S1 is going to be -1, and the reward at state 0 is going to be 1. It catches the fly, right? And once it arrives at state 0, I'll just call this 0, right? Once it arrives at state 0, the game is over. So I'll just call it, it's going to stay at 0. It's going to sit there happily eating the fly. Now, this is still the same system, right? But now let me introduce agency into the process. So do you see how the 2 systems are the same, right? This is just, I just redefined the system. I can in fact redefine my Markov reward process entirely in terms of these 4 states. But now let's do this fun stuff. The spider can take intelligent actions. What are the 2 actions it can take in this new definition of the system? It can either take an action which gets it closer to the fly, or takes an action which takes it further away from the fly. These are the only two actions it can take at any corner. There is no action in this setup where it can stay the same distance from the fly, right? So there are only two actions. But then here is the behavior of my spider. How does the agent respond? So now the spider is going to actively take some actions, and the fly is going to respond. If the spider is moving away from the fly, this fly does nothing. Who cares? You can go to Philadelphia, I'm safe. But if the spider begins moving towards the fly, what will the fly do? It's going to jump, right? Now flies know to jump, but they're not that smart. It's going to jump randomly. It's going to jump out. The only thing it knows is that it's unsafe at the current corner. So it's going to jump, and it's going to randomly pick one of the other 3 adjacent corners to go to, in my definition of the game. So if the spider is moving towards it, it randomly hops to a different corner. But see the outcomes. 2/3 of the time, it actually increases the distance to the fly. 1/3 of the time, it's going to decrease the distance to the fly, right? This still increases the life expectancy of the fly, because 2/3 of the time it's going to move away, right? In spite of being random. So it actually looks like the fly is intelligent and just made a mistake, but really it's just being random. It's responding to a stimulus, right? And now let's model the system, right? Here's what happens. If the spider is at a distance of 3 from the fly, right? There's only one action it can take. No matter which way it goes, it's going to get closer to the fly. So what happens at that point? When the spider begins moving towards the fly is going to jump. So let's say the spider, so let me actually redraw this figure over here. And let me redraw the figure over here. So I have this, I'm really bad at drawing cubes. I've been trying to draw a decent cube for years, and I can't do it. So you'll have to bear with my abysmally horrible cubes. Okay. So let's say the fly is out here. And this is the spider. The distance is 3, correct? Now, regardless of what this spider does, the spider is going to reduce the distance to the fly. So let's say that this spider decides to walk in this direction and ends up at this corner. What is the fly going to do? The fly is going to jump, and the fly is going to jump, and it's going to either end up here, or here, or here, correct? So when it does that, what happens to the distance of the spider, of the fly from the spider? 2/3 chance, or maybe I got it wrong. So if it's going to jump, this fly goes here. It's actually, I got that wrong. At 2/3 chance, it's actually going to shrink the distance in this case, right? 1/3 is going to increase the distance. But let's assume I'm right, okay? In my magical world, I'm right. So in this case, what really happens? Here is the actual state transition probability matrix. If the current state is S3, you're going to stay at S3 with a probability of 2/3, and you're going to S2 with a probability of 1/3. Make sense? Right? I mean, not really. It's going to be 1/3 and 2/3, but you get the idea, right? Now, let's say the spider is at a distance of 2. If the spider is at a distance of 2, and the spider decides to move away from the fly is not going to do anything, right? So with a probability of 1, the distance increased from 2 to 3. So this is the actual transition that happened. P S3 given S2 is 1, P S0 and S1 given S1 are 0, right? But suppose it decides to move towards the fly. What happens? Same thing. The fly is going to jump. 2/3 of the time it's going to maintain the distance. 1/3 of the time it's actually going to get closer to the spider, right? So now P S2 given S2 is 2/3, and P S0 given S2 is 1/3. Make sense to you guys? So look at it this way, right? So back here, now let's say this is the fly, and this is my spider. If the spider moves in this direction, the fly's responses are still the same, right? 1 term out of 3 is going to actually get gobbled up. 2 terms out of 3 is going to end up at a distance of 2. Right? So depending on the action of the spider, the transition probabilities changed. Did you see what just happened over here? The transition probability, the environment's behavior, the environment state transition probability was a function of the action taken by the agent. Same thing if it's at a distance of 1. So if now let's say the spider is out here at a distance of just 1. So if the spider decides to move away from the fly is not going to move. So with the probability of 1, you're actually going from S1 to S2. No biggie, right? But if the spider decides to move towards the fly, what happens? The fly jumped. It moved 1 edge away, right? What is the resulting distance of the spider from the fly? Still 1, right? Because it got to the fly, but the fly moved away. So now the set transition. So in other words, if you have if the spider is moving towards the fly, P of S1 given S1 is 1. So again, you see that the transition probabilities are now dependent on the action of the agent, right? And something interesting that you will observe over here is walking towards the fly the most optimal thing to do? No, because if you're at a distance of 1, if you move towards the fly, you're never going to catch it. The spider, that spider is a dead guy, right? In fact, when it's at a distance of 1, the correct thing to be doing is to be going away from the fly and then getting back towards the fly, right? And that's when it has the maximum chance of catching the fly. So this is clearly not the optimal thing to be doing. So this is a simile for many problems in life: driving, stock market, advertising. The agent's conscious actions are going to change the environment, and the environment is going to change in a stochastic manner. In other words, the state transition probability for the environment is a function of the agent's actions. Make sense to you guys? So this is, I mean, I wanted to make sure that the whole concept was not abstract, to actually see an example where this actually happens, although it's a toy example, but you know, it's got analogies. So this is a Markov decision process. A Markov decision process is a Markov reward process where the agent has the ability to decide on the action, on an action. We're going to represent individual actions as A, with action taken at any time t as AT, and the agent's actions affect the environment's behavior. And the transitions made by the environment are functions of the actions. The rewards returned are functions of the action. I spent way too much time on this particular set of slides, but these are the most key components of the whole thing. So formally, a Markov decision process is this tuple, which includes the state, set of states, set of actions now, transition probabilities, you know, the discount factor, and now this is an action conditioned reward function. In other words, the reward that you get is not just dependent on the state that you're in. The reward that you get depends on the state that you're in, but action that you took. In the particular example that we had for the spider and the fly, the action didn't actually decide the immediate reward. The reward just depended on the state. But in a more generic setting, you can imagine that, you know, if I actually have little, tiny little swarms of flies on each of the edges, you're going to have an action dependent reward function, right? So the reward is dependent on both the action and the state. So now we introduce the notion of a policy. A policy is the probability distribution over actions that the agent may take at any state, right? So here, for example, the spider is in the top left corner, right? What are the actions it can take? It has only 2 actions: reduce the distance or increase the distance, right? Or if you define my information state as the corners of the cube, there are 3 directions in which it could go. There are 3 possible actions, and so I can define a probability distribution over the actions. And this policy may be deterministic. So for example, you may say that if I'm in, so here is an example of a deterministic policy. This deterministic policy is going to say that if I'm at C1, I'm always going to go towards C3. If I'm at C3, I'm always going to go towards C5, right? So over here, I have, let's say I define my actions like so. 1, 2, 3, 4, 5, 6. So 1, 2, 3, A3, A1, A2, A4, A5, A6, right? So P of action given state equals C1 is going to be, the only action allowed is this guy, right? Delta of A4, meaning the probability of action number A4 is 1 and all other actions have probability 0, right? So this is not a particularly good policy for the spider. It's going to be wandering around for a long time before it catches the fly. But you get the notion of a policy, right? A policy is the action that the agent decides to take at in any state, and this action can actually be deterministic or can have a probability distribution. So what are the actions? Suppose the spider, what are the action-dependent transition probabilities for the states over here in this case? What is the transition probability from state? If I'm using the 8-state definition for the information state, what is the transformation to transit? So I have a policy. I've defined the policy over here, right? So now the policy actually decides what actions the agent is going to take. What will the transition probability for this system be? So what is P of C3 given C1? You know that when the spider is in C1, it's always going to go towards C3, right? So P of C3 given C1 is 1. But all the others, it's 0, right? What is P of C3 given C5? 0. Because from C5, only C4 has a probability of 1. So the transition probabilities now become dependent on the action, right? So transition probabilities become dependent directly on action. It actually indirectly becomes dependent on policy. If you have a probability distribution over policies, you'll get an overall transition probability. But the way we have defined it, the transition probability, any specific action is going to change your transition probability. Here's a different example of a policy, right? In this case, if I'm at C1, I'm going to go to C2. If I'm at C2, I'm going to go to C8. This is more optimal. You're taking the shortest path to the fly in each case, right? This is an optimal policy. So what are the transition probabilities here? Again, they're going to be deltas at each corner, right? And it's very easily defined. Okay, so what happens is if you follow this policy, and assuming that you pay a cost of -1 for walking on an edge, what is the expected return for being in corner C1? Anyone? What is expected, assuming that catching the fly is 0, right? What is the expected return for being at corner 1? -6. You have to take 6 steps, right? What about corner 7? It's 2, right? -2. On the other hand, if I were using this policy, what is the expected return for being at corner C1? -2. So what we observe is that the expected return from any state depends on the policy you follow, right? If I change my policy, I may expect to get a different set of rewards. And so one way to think about it is look at it this way. So suppose these are the actions I decide. My policy says that when I'm at S1, I'm going to try to reduce the distance. If I'm at S2, I'm going to reduce the distance. If I'm at S3, I'm going to reduce the distance, right? Now here are the transition probabilities that you have to worry about. The others, right? So now if I go back and write my Bellman expectation equation, what is the value of being in S1? It's the reward for S1 plus the expected return for over the states, the discounted expected return that over the states that I will actually get to, right? And I know that from S1 I'm always going to get back to S1. So the value of S1 is going to be the reward at S1 plus gamma times the value, right? And observe that in this case, the whole thing is a closed loop. It's basically a negative, very large negative reward because you're never going to catch the fly. Similarly, over here, if I'm in S2, what is the value of being in S2 considering that I'm always going to take the action A minus? It's going to be the reward for being at S2 plus gamma times the expected reward, expected value of the states that you can actually get to from S2, right? And from S2 you can either get back to S2 or to S0. So the value of S2 is going to be the reward at S2 plus gamma times 1/3 value of S0 plus 2/3 value of S2, right? Same thing over here. Here there's only one action I could possibly take, I get exactly the same kind of equation. Now suppose I change my policy and do this instead. The equations that I will use actually changed, right? Now what is the value of being at S1? The value of being at S1 is the reward at S1 plus gamma times the value of S2 because I'm going to go to S2 uniquely, right? But for these two guys, the value function stayed the same. Now I can also do something else. Instead of having a deterministic policy, I can have a stochastic policy, which is if I'm at S1 2/3 of the time, I'm actually also trying to confuse the fly. Let's say the fly is slightly smart, right? I'm trying to confuse the fly. So 2/3 of the time I'm going to increase the distance, 1/3 of the time I'm going to decrease the distance. If that is the case, then what is the expected value? What is the value of being in state S1 in this case? Anyone? How would I write it? Basically, it's going to be 1/3 the reward of S1 if I took this action, plus 2/3 the reward of S1 if I took this action. Correct? Same thing for each of the three guys. You get the, you understand, you get the concept here, right? It's very simple. So again, the action determines the transition probability, and effectively, the policy determines the transition probability, but it's easier to say the action decides the transition probability. And because the transition probability decides the return, expected return at every state, so the policy decides the expected return at every state, which is simply going to be an average over all actions of the probability of that action times the value of the state, assuming you're going to take that action every time from that state, right? It's a very simple notion. So this is what we'll call the state value function for a Markov decision process. It's the expected return from any state, and this depends on the policy that you follow. So I'm going to say, so to show that the value of any state depends on the policy, I'm going to use a subscript pi, where pi is a policy, and actually pi is a complete probability distribution over all actions from every state. It's a lot like a transition probability matrix. Except instead of deciding future states, you're actually choosing actions. So pi is a p of a given s. It's a probability distribution of actions from any state. And so the value for any state is going to be the average over all actions, right, times the value the state would have had if you chose that specific action. And so observe now that the reward is indexed both by the state and the action, right? And the value for this subsequent state, again, only depends on the state, but this transition probability, again, is action dependent. Right? We just sort of encapsulated everything that we wrote, that we explained so far. The value for any state is the sum over all actions of the probability of choosing that action from the state times this guy, which is the reward at that state for that action, plus the discounted expected reward at the next expected value of all of the states that you're going to get to using the transition probabilities that were derived from that action. Right? This is what we will call the Bellman expectation equation for state value functions of a Markov decision process. This is the one, the Bellman expectation equation. This is the key term. Okay. So now observe that this term over here was action specific, right? And I averaged it over all possible actions. So I can actually define things slightly differently. I can define things in this way. I can say if I'm in state S1 and I take the action A plus, this is the value for the state, right? If I'm in state S1 and take the action A minus, this is the value for the state, right? So now I can assign values for the state which are a function of both the state and the action. Each of the arrows is actually a value which depends on the action, correct? So based on this, I can now associate value to state action pairs. This is the value for state S1 if I take the action A plus. This is the value for state S1 if I take the action A minus, right? And observe that this value, which I'm representing using Q, is the current reward plus the discounted expected value over the future states, but this is the action independent value, right? You're just saying that if you're basically saying that if I'm in S1, what is the value? If I'm in S1, then it's whatever reward I got plus the value of this guy, average of the values of those two guys, right? So the state action value is going to be the current reward plus the expected value of the future states. So I can actually write this equation out like so. This is the Bellman expectation equation for action value functions of a Markov decision process. The value associated to any state for any given action is going to be the reward for that action at that state plus the discounted expectation over all future states of the values of the future states. Note that this is a V and this is a Q, right? This is the way you saw this from the figure. This is how the whole thing actually is going to work out, right? And so I can encapsulate the whole thing. I can write the whole thing in two ways. So this was the standard Bellman expectation equation that we wrote earlier, where we define the value of a function, value of a state, as the expected value over all actions of the reward for the action plus the discounted expected future value. The action value for any state action pair is simply the reward for that action from that state plus the expected value of all future states. But this guy is simply the term within the parenthesis, right? So I can write it down, obviously. The value for any state is going to be the average of all of the action value functions for that state, right? So this is both intuitively obvious and derives directly from the first two equations. And conversely, now I can define the action value function for any state entirely in terms of action value functions for the future states, where all I've done is to replace this V term by the expansion in terms of action value functions for the future states. Okay, this is a complete set of equations. Okay. Now, so these are the two Bellman expectation equations. This is the Bellman expectation equation for the state value function. This is the Bellman's expectation equation for the state action value function. Again, this is just for a quick reference, but you get the notion of exactly, it should be fairly trivial to derive these formulae once you understand what is going on. Right, now what was the purpose of all of this? Given a complete definition of a Markov decision process, we wanted to assign the values to each state, or we wanted to assign values to action at each state. And from the definition of the process, I've given you a bunch of simultaneous equations through which these terms can actually be computed, right? So when I speak of solving an MDP, this is my slides. These slides are kind of outdated. I'm not sure exactly what happened. So, but when I'm speaking of, the term really shouldn't be solving, but let's say I'm speaking of computing an MDP, right? If I'm speaking of computing the value of a Markov decision process, what I'm really saying is that I'm given the complete MDP, which means I'm given all the states, I'm given the complete specification of action-dependent transition probabilities for all states. So for every state action pair, I give you the complete transition probability matrix, right? And I also give you the rewards, state and action dependent distribution over rewards, or the expected reward for every state action pair. And I give you the discount. And I give you a policy pi. So I've given you everything about the process. Here are the states. Here are the actions you can do. And from this state, if you perform this action, here are the transition probabilities. Here is the probability distribution over all actions for the state. Here is the discounting factor you must use. This is how much you can trust what you observe of the future. Given all of these, you now want to compute the value for the states. You basically are the spider, and you want to assign a value for dropping at each corner, right, and the cube. And that process is what we will call computing the value of an MDP. Not so much solving, but computing the value for an MDP. The Bellman expectation equations are simultaneous equations that must be solved, and these are going to be computationally intractable for very large spaces. I will stop right here, and we'll actually talk about optimizing MDPs and such like in the next lecture. If you have any questions, post in Piazza, right? Thank you.